Welcome back. This will be a short video lecture on Section 4.1, Introducing Hypothesis Tests. Now, I've broken this section up into 4 parts. First, we'll look at testing versus estimation. Then we'll look at questions, claims, and evidence. We'll follow that up with some examples, and then we'll close the section with just a few remarks on statistical tests. So let's begin with testing versus estimation. In statistical inference, we use data from a sample to make conclusions about a population. The 2 main areas of statistical inference are estimation, which we covered in Chapter 3, and testing, which we will study here in Chapter 4. So let's think about a typical question in estimation. For men and women, what is the difference in the means of the numbers of hours spent exercising per week? Now, we locate this parameter within a confidence interval. In testing, we ask questions like, does leaving a light on at night affect weight gain? Here we conduct a hypothesis test and weigh the evidence, and we are required to draw a conclusion. So while estimation and testing both fit under the heading of statistical inference, they feel very different, right? In estimation, we're being asked to locate a parameter. Tell me where on the number line I would find this parameter of interest. While in testing, we're being asked to answer a question. Does leaving a light on at night affect weight gain? We need to answer, yes, the evidence seems to favor this conclusion, or no, the evidence does not seem to favor this conclusion. All right, so this brings us to the topic of questions, claims, and evidence. Let's look at some common steps in research. Most research begins with a question, and that question is often of the form, does A affect B? Now, in order to study that kind of question, we have to make a claim. And these claims are made in terms of parameters. And by stating our claims in terms of parameters, we are opening our question up to statistical analysis. The next phase is evidence. We collect samples and generate sample statistics. The next phase is testing. We take the evidence that we've collected and we weigh it. We decide whether this evidence is weak or strong. Finally, we draw a conclusion. We answer the question, is there enough evidence to find in favor of our claim? Now we'll take up the topics of question, claim, and evidence here in section 4.1, and we'll leave testing and conclusion for the most part to later sections of chapter 4. Now, in statistics, we handle claims and evidence in a very peculiar way. And in order to understand this, it helps to think about why we need testing at all. So what is testing and why do we even need testing? So we need to study this question in order to understand the nature and shape of scientific claims. So we are often testing for the presence of an effect. Let's think about the following problem, right? What are the different factors that could be associated with success or winning in the National Football League? We can probably think of hundreds of things that have an impact on the outcome of a game. And here are a few. What are the weather conditions? What are the field conditions? How skillful are the teams? How do the teams match up with each other? So, for example, is one team's skill set on offense aligned with the other team's weakness on defense? What is the number of rushing attempts for each team? Which team is home and which team is away? So we get the feeling that if we could identify and quantify all of the relevant factors, then we could predict the outcome of a given game. But truth be told, there is a lot of random stuff that goes on in each game that can't be anticipated. It's not, strictly speaking, predictable. So why does all of this matter? Well, when we look at any one of these factors, we should not think of it as being perfectly effective. Each factor might have an influence, but its effect is not going to be absolute. It's just one of the many variables influencing the outcome of the game. Now let's consider a research question. Does the home team have an advantage in the NFL? Now we expect a yes or no for the answer, but what does this question mean? As it is, it's a bit vague and hard to quantify. We know from our experience that the home teams don't win all of their games, so what would we accept as evidence in support of the home team having an advantage? So let's sharpen this question. Let's introduce a parameter. Let P be the proportion of games won by the home teams in the NFL. Now we can rephrase this question as, is P greater than 0.5? Now, if the answer to this question is yes, then we can say that being the home team has an effect on winning games. Now, we will never be able to answer a question like this with absolute certainty, but we can look at the evidence and judge whether or not we should favor this conclusion. In order to fully understand how we might look at evidence and make a judgment in favor of an effect, we first have to understand what it means for a factor to have no effect. Let's look at a factor in football that would clearly have no effect. Suppose that before the game, a referee tosses a coin. If the coin is heads, then the home team must wear a tiny H sticker on their helmets, and the away team must wear a tiny T sticker on their helmets. And if the coin is tails, then the home team must wear a tiny T sticker on their helmets, and the away team must wear a tiny H sticker on their helmets. Now, to just make sure you've got this image firmly in your mind, let's imagine that in a game, the Pittsburgh Steelers are the home team. The referee tosses the coin. If it lands heads, then a tiny little H sticker is affixed to the Steeler helmet. And if the coin lands tails, then a tiny little T sticker is affixed to the Steelers helmet. Now, as before, we can ask the vague question, do the H teams have an advantage in the NFL? Does wearing the H sticker confer some advantage in the NFL? Now, as before, let's let P be the proportion of games won by the H teams in the NFL. We can rephrase this question in a much clearer way. The clear question would be, is P greater than 0.5? Now let's think about this. In each contest, the winning team has an equal chance of being labeled H or T, so in this case, the answer is no. In fact, P equals 0.5. This is what we will call the condition of no effect. We don't believe that the type of sticker worn on the helmet has any effect on the outcome of the game. Now, the real question for us, though, is what are the consequences of no effect? Let's continue with our example. So, let P hat be the proportion of games won in a season by the teams wearing H stickers on their helmets. So, in an NFL season, there are 256 games. So here is the sampling distribution for P hat. Each one of the dots in this diagram corresponds to a season's worth of games and the corresponding proportion of those games that were won by the teams wearing the H stickers. Now notice that the values of P hat form a bell-shaped distribution centered on 0.5, and that 95% of the P hat values land between 0.438 and 0.562. Now this means that even if a condition like wearing tiny H stickers on helmets has no effect, it can appear to have an effect. Let's look at it this way. In a given season, the teams wearing the tiny H stickers might win 52% of their games. And we might conclude without thinking that this provides evidence for an effect. We might say to ourselves, wearing an H sticker is advantageous. But should we conclude this? Isn't this completely consistent with having no effect at all? Now let's think about home field advantage. Suppose that the home teams win only 52% of their games in a season. Is this really evidence for an effect? I would say no, because winning 52% of the games is completely consistent with no effect, namely wearing tiny H stickers on helmets. In other words, on the basis of this evidence, Being the home team has as much effect as wearing a tiny H sticker on your helmet. So here's the important takeaway from this example. To show that something like home field advantage has an effect, we really need to show that we have evidence that is inconsistent with the no effect hypothesis. In other words, to judge the presence of an effect, we have to thoroughly understand the condition of no effect. So in fact, we must keep in mind two competing claims, the claim of no effect and the claim of significant effect, and we must learn to judge between them. In statistics, we give our primary allegiance to the condition of no effect. We sit there petulantly with our arms crossed. We are stubborn on this point. This is where we plant our flag, and only in the face of very strong evidence are we moved to favor the condition of significant effect. So in fact, we must be pulled like a stubborn mule. Now in statistical language, the condition of no effect is called the null hypothesis, and the condition of significant effect is called the alternative hypothesis. Let's take a look at these two concepts in some more detail. So here are the technical definitions of the null and alternative hypotheses. So the null hypothesis is often denoted by H sub 0 and it's read H naught. And this is the claim that there is no effect or the claim of no difference. The alternative hypothesis is often denoted by H sub A or sometimes by H sub 1, and this is the claim of a significant effect. Let's take a look at our example from before. Let P be the proportion of NFL games won by the home team. The null hypothesis is that that proportion is equal to 0.5. That's the condition of no effect. The alternative hypothesis is that P is greater than 0.5. That is the condition of a significant effect. And you'll notice that we always frame the null and alternative hypotheses in terms of parameters. Now let's study some of the very precise language that has developed around hypothesis testing. So in a hypothesis test, we begin by assuming that the null hypothesis, or H naught, is true. The sample data gives us our evidence. This evidence is either consistent with or inconsistent with the null hypothesis. We conclude one of the following. If the evidence is consistent with the null hypothesis, then we fail to reject H naught and conclude there is not sufficient evidence in favor of or in support of the alternative hypothesis. Now, if the evidence is inconsistent with the null hypothesis, then we reject the null and conclude that there is sufficient evidence in favor of or in support of the alternative hypothesis. Now, to help you fix these concepts in your mind, let's go back to a previous example. So, let P be the proportion of NFL games won by the home team. The null hypothesis, the hypothesis of no effect, is that P in fact is equal to 0.5. The alternative hypothesis is that P is greater than 0.5. Now let's consider two cases. Suppose that after the season has finished, we find that the home teams have won 52% of the games. That's a P hat of 0.52. Now, as we have seen before, P hat equaling 0.52 is rather consistent with the hypothesis that P is equal to 0.5. So in this case, we would fail to reject the null, and we would conclude that there is not sufficient evidence to favor or support the alternative hypothesis. On the other hand, suppose that at the end of the season, the home teams have won 80% of their games. Now, we would find that rather inconsistent with the claim that P is equal to 0.5, and we would now reject the null and conclude that there is, in fact, sufficient evidence to favor or support the alternative hypothesis. Now, when we fail to reject the null hypothesis, we're not saying that it's true. All we're saying is that insufficient evidence has been produced to cause us to favor or support the alternative hypothesis. And when the evidence causes us to reject the null hypothesis and favor or support the alternative hypothesis, we're not saying that the alternative hypothesis is true. We're just saying we now favor it, we support it, we find it compelling, but we're not saying that it's necessarily true. Now, we will discuss this at greater length in the coming sections, but let's talk a bit about the direction and strength of evidence. Now, as before, let's let P be the proportion of games won by the home team in the NFL. Our null hypothesis is that P is equal to 0.5, and the alternative hypothesis is that P is greater than 0.5. Now, where are we going to look for our evidence? Well, we're going to watch an entire season of NFL games. There are 256 games in total, and we are going to let P hat be the proportion of those games won by the home team. Now, we know that P hat will have to fall between 0 and 1. It's going to land somewhere on this number line. But I claim that this automatically is going to divide our number line into two pieces. There's the piece between 0 and 0.5. If P hat lands between 0 and 0.5, I claim that that provides no evidence in favor of the alternative hypothesis. So, for example, if at the end of the season the home teams have won only 48% of the games, that provides us with no evidence at all in favor of the claim that P is strictly bigger than 0.5. On the other hand, if P hat lands between 0.5 and 1, there's some evidence in the sample supporting or in favor of the alternative hypothesis. So for example, if the home teams win 58% of their games, that's pointing in the right direction. That is some evidence in favor of the alternative hypothesis. Now, I claim that this interval from 0.5 to 1 needs to be further subdivided into two cases. All right? If P hat is greater than 0.5 but near to 0.5, then we might call this evidence weak. Now, it points in the direction of supporting the alternative hypothesis, but it is consistent with the condition of no effect. In other words, this evidence is hard to distinguish from no effect. And so this might happen, for instance, if the home teams win only 52% of their games. Now, our intuition tells us, however, that as the value of P hat moves closer to 1, then the evidence for P greater than 0.5, the evidence for the alternative hypothesis becomes stronger. So imagine that the home teams win 70% of their games, or 80% of their games, or 90% of their games. We feel that the evidence for the alternative hypothesis is becoming stronger as the value of P hat marches closer to 1. So we reach a point where the value of P hat is no longer reasonably consistent with the condition of no effect. And in the face of this kind of evidence, we feel confident to reject the null and favor the alternative hypothesis. In other words, the evidence becomes very strong. Now, where is the crossover point from weak to strong evidence? This will be a topic of later sections. So at this point, let me just say that a test is run at what's called a significance level. And once we know the significance level of the test, then the threshold that divides the weak evidence from the strong evidence can be easily determined. Now, I'll work some examples with you in just a bit, but before we do that, I want to do a little bit of fine-tuning, so I've put together 5 things to ponder. Point number 1. The null and alternative hypotheses are claims about population parameters. They are not claims about sample statistics. So always be careful to phrase the null and alternative hypotheses in terms of parameters. Point number 2, sample statistics provide us with the evidence to judge claims. So if we take points 1 and 2 together, both parameters and sample statistics have a role in testing, but they are very different roles. Point number 3, in general, the null hypothesis is a statement of equality, while the alternative hypothesis uses notation indicating greater than, not equal to, or less than, depending on the claim of significant effect. Point number 4, if the evidence is weak, then we do not reject H0. And this is not the same thing as accepting H naught. And this type of distinction can be found in our legal system. So let's say Joe is on trial for murder. The null hypothesis is that Joe is innocent, and the alternative hypothesis is that Joe is guilty of murder. Now, if there is not strong evidence for Joe's guilt, then we say Joe is not guilty, and we are careful not to say that Joe is innocent. Finally, 5. The burden of proof is on marshaling strong evidence for the alternative hypothesis. In other words, if you want to show that an effect is significant, you must produce strong evidence. At this point, I just want to remind you of some common population parameters and their corresponding sample statistics. You can see them in the table here. You're familiar with all of these, so I won't bother reading through this table with you. I just want to remind you, though, that you will always be phrasing your null and alternative hypotheses in terms of the population parameters, and you will be seeking evidence in the corresponding sample statistics. So if a null or an alternative hypothesis are being phrased in terms of the parameter rho, you will seek evidence in the sample statistic R. Now, what I want to do is work a problem with you that I hope will draw out a lot of the elements of the things that we've been talking about up to this point in this section 4.1. So let's take a look at this problem together. We'll work it over at the document camera. All right, so welcome to the document camera. In each case, indicate the statistic to be studied and what would constitute evidence in support of H sub A. Well, in this first problem here, we see that we're given the null hypothesis is that some proportion is equal to 0.3, and the alternative hypothesis is that proportion is in fact greater than 0.3. Now, since we're working with a population parameter of a proportion, the sample statistic that we'll use is going to be a p hat, a sample proportion, and what we would accept as evidence in support of the alternative is any value of p hat that's in excess of 0.3, okay? And we understand that as that p hat grows from 0.3 to 1, the strength of the evidence will be increasing. So in other words, a p hat equaling 0.8 will be stronger evidence in support of this than a p hat equaling 0.5. Okay, in the second problem, our null hypothesis is that some population mean is equal to 4, and the alternative hypothesis is that that population mean is greater than 4. And since we're dealing with a population mean, our sample statistic is going to be a sample mean, and in order to find evidence in support of the alternative, we would be looking for that sample mean to exceed 4 as well. Okay, understanding that as the value of x bar increases beyond 4, as the value of x bar is increasing, the strength of the evidence in support of this alternative hypothesis is getting stronger. Okay, this problem 3 involves two different population parameters. So we've got a mean from a population 1 and a mean from a population 2. The null hypothesis is that those are the same. They have the same value. And the alternative hypothesis is that mu1 is less than mu2. Now, what I find helpful anytime I'm comparing two different population parameters, I find it helpful to rephrase the null and alternative hypothesis in terms of a difference of two parameters. So in other words, I just want to take the difference between mu1 and mu2 in some order, and it really doesn't matter the order you pick, but choose an order and rephrase h0 and ha accordingly. So let's do mu2 minus mu1. So I would rephrase h0 as, I'll write it underneath here, I would rephrase h0 as mu2 minus mu1 equals 0. And I would rephrase the alternative as mu2 minus mu1 is positive, because mu2 being greater than mu1 is the same thing as saying mu2 minus mu1 is positive. So this imposes direction on the problem, and that's going to help us think our way through what we're looking for in terms of evidence. Okay, so now what are we going to look for evidence? Well, since these are both population means, I'll have to use corresponding sample means. So I'll expect a sample coming from population 2. I'll look at its mean. I'll expect a sample coming from population 1. I'll look at its sample mean. And since I'm taking the differences mu2 minus mu1, I will take the differences in exactly the same order, and I'll look to see if the sample means, well, the difference in sample means is positive. Okay? All right, finally, we've got a problem involving a correlation. So our null hypothesis is that some population correlation is equal to 0, and the alternative hypothesis is that that population correlation is different from 0. So this is a case that's a little bit different than any one that we've worked already, so we'll see a very different answer for this last part. Okay, so since we're working with a population correlation, of course we would expect to work with a sample and a sample correlation. So that's going to be our corresponding sample statistic that's paired up with our population parameter. Now, what would be evidence in support of rho not equaling 0? Well, in this case, we'll accept two different types of evidence. A sample correlation that's less than 0, or a sample correlation that's greater than 0. Either of those will provide us with evidence that the population correlation is different from 0. So the language of art for this is called a two-tailed test, because we'd be looking for evidence in either direction, either to the left of 0 or to the right of 0. And these are all called one-tailed tests. Okay, so that completes this problem. And let's go back to the class notes. In this next subsection, I just want to work through 3 examples with you. In each of these examples, we'll begin with a scenario and a question. Then we'll pull the relevant parameters out of the question and articulate a null and alternative hypothesis. And then finally, we'll look at various types of evidence and try to gauge its strength. So join me over at the document camera to study these 3 examples. Okay, so welcome back to the document camera. Let's take a look at a sequence of problems. First, the American Heart Association recommends at least 2.5 hours of exercise per week. The vice president for student life at Chutney State University is concerned that the students are not getting enough exercise. She wonders, on average, do the Chutney students not meet the AHA's recommended minimum requirement for weekly exercise? All right, so that's the question of interest. What parameter is under investigation? Well, if we read into this question, she's worried about a population mean. She's worried about what we could call mu, which we could say is the average or mean hours of exercise per week for the, let's call them the CSU, the Chutney State University students. Okay? All right, so that's our parameter of interest. Formulate the null and alternative hypotheses. Well, remember that she's concerned that the students aren't getting enough exercise. That's what she's testing. And so we would certainly identify the alternative hypothesis that mu is less than 2.5 hours, and that the null hypothesis is that mu is equal to 2.5 hours. All right, so a random sample of 100 Chutney State students were surveyed. Let X bar denote the sample mean of their exercise times in hours. In each case, determine whether X bar provides evidence in support of HA. Now, what we have to understand is by reason of how our null and alternative hypotheses are phrased, that effectively we have a number line. And on that number line, we would find 2.5, let's say here. And we would know that any value of X bar that's landing on this side of 2.5 is not providing any evidence in support of this significant claim here, right? So we would say that on this side, there's no evidence. And on this side, there's evidence. Now, in this case, let's just remind ourselves, in this case, we would see that as this value of x bar drops down closer and closer to, let's say, 0, the evidence in support of this claim, this exceptional claim or this significant claim, is actually getting stronger. Okay, so we not only would we say that this on this side is where the evidence in support of HA exists, it's also getting stronger in this direction towards the left. Okay, let's take a look at each of these cases. So suppose that they sampled 100 students and they found that, in fact, they averaged 3.8 hours per week. Well, we would find that on this side of 2.5, and so we would say that 3.8 does not provide evidence. I'll just indicate that by NE for no evidence. What about 5.2? Same thing. 5.2 is to the right of 2.5. That would not be supporting the claim, and so we would say that 5.2 also provides no evidence. Well, what about 1.8? We would find 1.8 over here, and we would say that does provide some evidence. Now, whether that's strong evidence or weak evidence is to be determined, but at least it's pointing in the right direction. It's some evidence in support of the alternative hypothesis. So 3.8 and 5.2 are both on this side of 2.5. No evidence associated with those x bars. 1.8 is to the left of 2.5. There is some evidence in support of the alternative hypothesis for that value of x bar. Okay, let's look at the next problem. Okay, let's take a look at this next problem. Workers at a popular fast food chain are supposed to fill the drinks up to a line on the side of the cup, which corresponds to 12 ounces. The manager wonders, does the average volume of soft drink dispensed by the workers differ from 12 ounces? Okay, part 1. What parameter is under investigation? Well, here we can basically read it right out of the question. What the manager is concerned with, the population parameter of interest in this case, is a mean, mu, which we can say is the average volume, and we'll say in ounces, of soft drink dispensed by the workers. And now we have to formulate the null and alternative hypotheses. So we would simply say that the null hypothesis is kind of the no effect hypothesis. Everything is fine. That the mean level is 12. The workers are doing a great job. The alternative hypothesis, though, and we have to be a little careful in this case, is does the average volume of soft drink dispensed by the workers differ from 12 ounces? So she's concerned about underfilling, coming up less than 12 ounces, and she's also concerned about overfilling, exceeding 12 ounces. Both of those would be a problem if they were really rampant. And so she's concerned with testing the claim that mu is not equal to 12. Okay, now, this is a classic two-sided test, and so we have to be careful how we think about the evidence. So, a random sample of 200 soft drinks were sampled. Let x bar denote the sample mean of their volumes in ounces. In each case, determine whether x bar provides evidence in support of this alternative hypothesis. Now, here's what it looks like. We've got our number line, and there's the 12 ounces that comes from the null hypothesis. Now, because our alternative hypothesis is simply mu not equal to 12, in fact, in this case, we'll find that both sides of 12 provide us with evidence in support of this alternative hypothesis. So, in fact, on both sides, we would mark both sides as providing evidence. Okay? Now, the further away x bar is from 12 in either direction, the stronger the evidence. Okay? But in fact, anything other than 12 is going to be evidentiary, right? So 12.5, does that give us evidence? Yes. Let's mark that as E for evidentiary. Does 11.5 give us evidence? Sure. How about 13.1? Yes. Let's do a little follow-up question. So 12.5 might put us here. 11.5 puts us equidistant on the other side, and 13.1 puts us, let's say, right here. So we've got 12.5, 11.5, and then we've got 13.1. Which one of these is actually giving us the strongest evidence in support of HA? Well, it's the one that's furthest away from the null hypothesis or the hypothesized mean of 12. So, in fact, this one is giving us the strongest evidence of the alternative hypothesis. Okay, we've got one more problem like this that we're going to look at, so let's take a look at that problem. Okay, let's take a look at this final problem of this type. The academic dean at Chutney State is concerned about student grades. She wonders, is class attendance positively correlated with final exam score? So, part one, what parameter is or what parameters are under investigation? Well, we can see by the nature of the question that it's a correlation, and it's a population correlation. So we're going to use rho to denote this parameter. And how would we articulate this parameter? So rho is the correlation. Let's say the correlation between, let's say, the number of days in class and final exam score. Okay, let's say that the final exams are scored on some kind of uniform scale from 0 to 100. All right, and the number of days, you just count the number of days that a student was in class. Okay, so what parameters are under investigation? It's this correlation. All right, formulate the null and alternative hypotheses. Well, she wants to know, is class attendance positively correlated with final exam score? So our alternative hypothesis would be that correlation, in fact, is positive, and the null hypothesis would be that the correlation, in fact, is 0. Okay? All right, that there's no correlation between them. The records of 100 randomly selected Chutney State students were retrieved. Let R denote the sample correlation between their days attended class and the score on the final exam. In each case, determine whether R provides evidence in support of the alternative hypothesis. So once again, we just have to look at the situation and realize that the 0 is going to be our dividing line, and that on this side of 0, on the positive side of 0, we'll find evidence in support of the alternative hypothesis, and on this side of 0 to the left, we'll find no evidence in support of HA. Okay? So let's take a look at this first one. If we looked at the sample of size 100 and we found a correlation, a sample correlation of 0.25, that would land us on this side, and so we would say, yes, that provides us with evidence of a positive correlation. If, on the other hand, we saw that R was equal to negative 0.1, that would not provide us with evidence of a positive correlation. So we would say there's no evidence of a positive correlation. If R is equal to 0.69, that would put it, let's say, out here. And there we would find evidence in support of the positive correlation. And between these two, both of these are providing us with evidence of the positive correlation, but we also know that since this one is further from the null parameter, it's stronger evidence. So the 0.69 would be stronger evidence than the 0.25 in support of this alternative hypothesis. Okay, so that brings a close to this sequence of problems that I wanted to investigate concerning this issue of identifying parameters, formulating null and alternative hypothesis, and examining the strength of evidence. So let's return to the class notes and pick up where we left off. I want to close section 4.1 with a final parting thought, and this concerns the nature of statistical tests. So a statistical test is used to determine whether results from a sample are convincing enough to allow us to conclude something about the population. A claim does not pass the test without significant support from the evidence. And with that thought, I want to bring a close to section 4.1. Let's meet again when we study section 4.2. Until then, take care.